Hi there, my name is Rohan Ramani, and this is my CSD 3.5 final analysis. So let's look at our problem number one, and our issue at hand currently is that we need to be able to read information from a config file. From the config file, we need to determine the data source, the type of parser, the filters, and the delay time in order to be able to build the rest of our project. Now, we don't want to parse the config file directly because the format and order might actually change. There could also be different parsing structures, and that would be very troublesome if we tried to parse the config file directly. And we also need a data structure that is good at representing hierarchies found in the config file. Now, we don't want to modify the data structure, but just extract information from it. So in order to tackle this problem, I used the visitor design pattern. So I should talk about the ANTLR parsing library because it creates a tree data structure, which is great for expressing hierarchies, and it's great for creating a recursive data structure, which is great for expressing nested expressions. Now, information is extracted by building a visitor, which visits certain nodes of the tree. So when an instance visits certain nodes of the tree, it could either visit a leaf node, which contains raw data. This raw data could be in the form of strings or integers or any other kind of information, really. Or it could visit a non-leaf node, which could contain information such as of other leaf nodes or other nested expressions, which would later have to be traversed down. So let me show you how the config file is built. So this is the config file, and the code example I'm about to show you has to do with the filter visitor. And so when we look at the code example, here we see the visit filter function. And this is a non-leaf node, which ends up calling one of these functions. So what we do is that we're basically passing in, we look at our selector and we accept and we pass in an instance of this visitor. And then it ends up calling one of these functions, a nested expression, and expression, or expression. A nested expression boils down to an and or an or expression. And as we can see, we are then passing in our visitor to the left of the and expression and the right, because an and expression takes in two parameters. So we're passing in our visitor to the left and right. And eventually what this is doing is it's traversing down the tree, and it is eventually going to get to a leaf node, which can, in our case, is the keyword expression. So here we're not actually going to be passing in our visitor, but rather we're going to be extracting the information from the leaf node. So it's just exactly what we're doing. We're calling .keyword, which is the attribute of that node, and then we're converting it to a string, trimming it, and returning it. So as we can see, this is how you traverse down the tree using the visitor pattern, and we're not actually changing the contents of the tree. We're literally just extracting the information held by the nodes of the tree. So what are the benefits of the visitor pattern? So why were we using it? So format changing is not actually a major problem. All you have to do is regenerate the contents from the ANTLR parsing tool. And actually, the config file was appended to for many times in the project, and that was not really an issue. All we had to do was add another visitor, and it's actually very easy to add another visitor and just extend the functionality of your whole project rather than having to rewrite a whole parsing algorithm or something like that. And we didn't have to modify any other classes. We just had to pass an instance of the visitor to an accept method. And we're not actually modifying the tree data structure that is returned by the ANTLR parsing tool, but rather passing an instance of the class that grabs the data. So what are the alternative approaches to the visitor design pattern? Well, we could have parsed the config file directly. Now, there's certain benefits for that, and which was that we wouldn't have to work with the tree data structure. Some people might not want to work with the tree data structure and might want to work with something easier, such as list. But it also might be easier for parsing tasks, which are smaller and more straightforward. For something that where you're parsing very small amounts of information, it might not be worth all the trouble to go and build visitors and such. But however, for any project where you're going to be appending to or some format and stuff is very, very important. The visitor design pattern is definitely the way to go. The drawbacks of the parsing the config file directly is that it does not represent any sort of hierarchy whatsoever. You might have to customly build your own hierarchy in that sense. And the formats could possibly differ, which could basically kill your entire parsing algorithm, and you might have to rewrite it every time the format changes, rather than having a tool that just generates a tree and then you go and visit the contents of that tree to be able to grab your information. So let's look at our problem number 2. And our issue at hand is that we want to actually be able to process our data and perform different actions with it. Things we might want to do is extract items, filter the extracted items, order, and then filter the extracted items, and then or just order the extracted items. In the context of this project, however, the exact problem that I wanted to address was to be able to process a list of articles in a way without putting all of the code in one process itself. So let's look at the design pattern that I used to tackle this problem, which was the decorator design pattern. It allows to extend the behavior of the class dynamically without actually changing the behavior of the class. So it builds functionality on top of what the original class usually does. And the problem that we needed to solve using the design pattern, which we needed to add more functionality, was doing filtering and accepting delays and the caching functionality. So let me show you some code examples to express what I'm talking about. Here, this is my filter processor class, and as we can see, the filter processor has a reference to the extraction processor. And in fact, you actually end up passing it into the constructor of the filter processor. And when the filter processor calls process, one of the first things it does, it calls the process function of the extraction processor, and then it uses a stream to filter certain items out of that list of articles using a filter expression. So we can see that the filter processor actually has a reference to the extraction processor. Just like that, we can see that the cache processor here in this code example actually has a reference to the filter processor. And again, one of the first things that the process function for the cache processor does is that it calls the filter processor process function, and then it implements all the caching functionality and whatsoever. And last code example for this problem was that even when, I guess you could see that when I'm building the filter processor or the cache processor, it's actually taking in a new instance of the filter processor here. So it's sort of built like a Russian nesting doll, where the smallest doll would be the extraction processor, and on top of that, it would be a filter processor, and then a cache processor on top of that. So yeah. What are the benefits of this decorated design pattern? One of them is that it showcases the single responsibility principle. Each decorator had only one task, which was to process the articles in a particular way. And it showcases the open-close principle, where classes are actually open for extension in this case, but closed for modification. And that is shown because we are actually allowing it to be a reference or an instance variable of another class. However, we're not allowing it to be extended or something like that, or we're not extending it in this case. Now, it also gives a choice to the client in order for the order, for example. You could put a filtering, ideally, if you wanted to implement it in a way, you could have it such that the filtering processor is wrapping around the sorting processor, or the sorting processor wraps around the filtering processor. And these two would actually, the order actually matters, and we're giving the power to the client to decide what order they actually want it in. Do they want to filter and then sort, or sort and then filter? So that's something that's very beneficial of the decorated design pattern. Now, what was an alternative approach? It was that we could be adding all the functionality to one processor. So the extraction processor could just be a general processor. However, this is very naive in hindsight. Benefit, obviously, is that it's less code files and it might be easier to manage because all the code is in one processor. However, this violates the single responsibility principle. It gives the client less functionality because they might not be able to decide what order they want everything in. And when you try to refactor the code for further functionality, when you need to add more things, it becomes much harder. And one other thing that I was thinking about while writing this presentation and stuff was that we could have used inheritance, but the problem with inheritance is that there's a lot of compile time restrictions that could be placed, and that generally is not the case with the decorator. And so decorator is a very good approach for basically adding functionality without modifying the class directly. Now, finally, our third issue, we could look at our third issue was that we want to be able to filter certain expressions and only include articles that have certain filtered expressions. Now, filter expressions could be only keywords. They could be complex expressions, such as a keyword and a keyword, or a keyword or a keyword, or they could be composite expressions, which contain complex expressions and other complex expressions, and they're by some type of operator. So the design pattern that I used to tackle this problem was the composite design pattern, and the filter expression was actually designed like a tree, and the leaves of trees were actually keyword expressions, and the non-leaf nodes were composite expressions. Now, keyword expressions were simple objects, and composite expressions such as and or were actually composite objects. And basically, a composite object could contain either a simple object or a composite object, or both, really. All the different permutations. So the composite pattern seemed like a perfect fit for that. So let me walk you through a code example. In here, there's the binary expression class, and as its left and right operands, we can see that it's a filter expression and a filter expression right here. So that itself is composite because it contains two other filter expressions. However, it also contains an operator function, which is an apply, the apply instance variable right here. In the constructor for the binary expression, we can see that it takes the same thing and it evaluates based on calling the evaluate function right here. It evaluates the left and it evaluates the right, and then it returns the apply function based on what apply is set by the user. So if we look at, for example, the keyword expression, this is a leaf node on the tree. So what we do when we get to this leaf node is that we're primarily implementing our main functionality, which is evaluating to see if a particular article has a particular keyword that we have here. So we're basically taking the description and getting it in the lowercase form and seeing if it contains a keyword. And we're doing the same thing with the URL and the title. So that's something to do right there. And then the AND expression is not a leaf node in the tree. However, it's it could be a composite expression. And basically what it does is that it takes the two parameters, left and right, and it ends them together. And so this A and B could then be keyword expressions to see if that is the same, or to see if, and this would, A and B could be keyword expressions, or they could be other AND expressions or expressions. Basically, they'd be filtered or binary expressions, and they would be evaluated and they would be ANDed with each other to see if they both return true, both return false, or whatsoever. Now, what are the benefits of the composite design pattern? Well, it works really well with expressions, which can be expressed as trees, like the current example that I showed you. The expression structure can be expressed in such a way, such that leaf nodes being keyword expressions or the simple objects, and the non-leaf nodes are being the composite expressions that still need to be traversed down. So we can clearly recursively traverse down the tree, and we could possibly skip portions of the tree because if we have an or expression, for example, and we evaluated the left and already became true, we could skip the right part because we know that it doesn't really matter what that one is. So that's something cool we could do based on the composite design pattern, and we could utilize the tree-like structure that exists in this case. And an alternative approach to this was that I thought we could just put all the filters in a list and iterate through the list while filtering stuff out. And it could be considered better because it uses a simple list data structure and not a tree structure. It could possibly be very complex. And some of the drawbacks is that the structure of the expression is more suited for tree traversal because of the way it's just set up. And it's more intuitive to actually use expressions as tree structures. And so the composite design pattern actually works very well with things with objects that could contain references to objects of the same type or simple objects, and it could be expressed as a tree. So yeah, that seems to be it for my presentation. Thank you very much for listening, and good day.